Right, that's right.
Yeah, okay, thanks, appreciate it. Actually, that's a neat feature. Yeah, I'm gonna try it from that thing in the back.
All right, can you see my screen?
Yes, amazingly, we can. Okay.
One of those days, huh? Okay.
Great, so the next talk is gonna be by Vincent Helendor, and kind of very flexibly stepping up from, it's rescheduled from this morning, and he is going to talk about a systematic survey of large language models of source code.
Awesome, okay. So I cut this talk pretty substantially short from a longer version of it that I've given a number of times, because I think the audience here knows a lot of the stuff I'm talking about already. So let me just go through the background real quick. We've talked about scaling models plenty today, and it's especially related to transformers, and sort of the observation that there is this unprecedented kind of really predictable scaling with larger models and with more compute and more data. And the same is true for software. So before Codex came out, sort of last, let's say, Codex came out last June, but let's say last March or so, most models of code were order of a few 100 million parameters at best. And then bam, Codex comes out, 12 billion parameters, and within the span of really about a year, we're seeing models that are billions and billions of parameters. Some of the models, the biggest ones, aren't even on the screen. Palm is 500 plus billion parameters, and there's a coder version of that too. And so, Copilot is really kind of why we're here. Copilot as being powered by Codex. But one of the things that we, that especially I initially sort of felt was off about this is that it's closed source, and there were pretty limited details in the paper about how it worked and why it worked. And so I kind of set out to train a model of my own and see what it took, and then I teamed up with some of the other authors of this paper to evaluate that model and kind of make it into a bigger survey. So that's how we got here today. And so this is the paper, Systematic Evaluation of Large Language Model of Code. And we're really kind of asking, how do you train a good large language model? What about data, volume, and pre-processing steps, model size, parameters, what is the role? Is initialization, the Codex paper mentions starting from GPT-3, is that necessary? Training, sort of all sorts of different training hyperparameters. We're just kind of trying to study the whole big picture in this paper, and so hopefully that's a valuable kind of data point in this space. And so let me explain kind of like how we got there by talking about some of the models that already exist and sort of contextualize what we learned in the process. So the first one is obviously Codex, the first sort of many billion parameter language model for code. They initialized from a pre-trained language model, just trained to sort of a common crawl, a web corpus, and then they fine-tuned on about 160 gigabytes of Python, and they introduced this human eval benchmark with which everyone is familiar after the previous talk. And some of their findings are this really kind of log linear scaling once the model gets big enough, its ability to predict code solutions to natural language problems, scales pretty linearly with the size of the model, so very predictable and reliable. There's plenty of other findings in the paper that I thought was really interesting. One of those is that prompting matters. So even saying, write good code prompt can make the model change its behavior. And a reminder that these models are, in a sense, parrots, right? Sort of echoing back what they've seen. And if they see that some prompts are better than others, then they might just sort of echo that back as well. And then Code Parent came out. That was the first open source entry where they trained up to about 1.5 billion parameters on some 26 billion Python tokens from BigQuery. And they have a number of findings in the paper. Some of those are deduplication was really important. They learned that lesson pretty early on. Another is that they use windows of about 1,000 tokens because it's really expensive to work with larger windows. And we're sort of confined to the computing infrastructure outside of OpenAI, Google, Microsoft, whatever. Whereas Codex goes up to windows of about 4,000 tokens, and so that will play a role a little bit later. And so then we came out at CMU with Polycoder up to about 3 billion-ish parameters, and we trained it on 12 languages because we felt that in the open source model space there was kind of a gap where there were no models trained on a bunch of programming languages at once. So we picked kind of the top 12 most popular programming languages and balance our training data set, somewhat balance our training data set across those. And some of our findings, so we trained models of various sizes, and we find that we hit a pretty hard ceiling at 3-ish billion parameters. That took about 1.5 months on the lab server that I have here. And you really can't train for much longer or much larger than that. We provide a bunch of insights in the paper that I hope will be helpful. Some of them are about sampling temperature and kind of the relation between model size and temperature, going a little bit beyond the Codex paper. We had some results that were slightly different. But I think the big picture for us was that, on the right side, it actually outperformed Codex on C. So we conducted this really broad, we took a bunch of models, including our own, and we asked it to compute the entropy of a bunch of held out test files in various programming languages. And so the entropy, just to remind you, lower is better in this case. So the closer to 0, the more kind of the file is predictable to the model. And so in one case on the C programming languages, the model was really quite good, the polycoder model, and that's in part because there was a lot of C in the training data. The bad news is that not only does Codex outperform it on a lot of other languages, which is to some extent understandable because it's bigger, and we don't really know if some of these files were in its training data. Even some models, to our surprise, some models that were roughly the same size as polycoder, but trained on far less code, they trained mostly on Wikipedia and whatever, web crawl data, could still outperform polycoder on a bunch of other languages. And that seemed really weird to us. And so we kind of set out to ask, what makes, and to some extent the other models work, because it really does seem unreasonably effective. We plot a scaling law here on the x-axis, we increase the number of parameters, and the model gets better. The blue line at the bottom, that's our model. But then the red line is Codex, and it doesn't just start off better, but it gets better much faster with more capacity. And so we were trying to figure out, well, what is going on here? One culprit might have been data pre-processing, so there's a lot of filters happening in the Codex paper. Some of them unclear, sort of underspecified perhaps. But then the CodeGen paper did a pretty good job replicating, a lot of those filters, and they didn't necessarily get better performance in the previous plot. In fact, its skill is even worse. So then we came up with two candidate explanations. One is this initialization. So Codex says it's initialized from GPT-3, which gives it some kind of head start. Now the Codex paper says this didn't matter to converge accuracy, but maybe there's something there. And then the other is these kind of training hyperparameters at the bottom, including the batch size, the number of training steps, the context window. And so to understand what's going on, we'll turn to another family of models. So let's look at these GPT, J, GPT Neo, GPT Neox models. These go up to about 20 billion parameters, and they were trained on this large web crawl, including GitHub. About 10% of their data is GitHub, and there's also Stack Overflow in there. And so they might provide a useful reference point. And so one of the reasons they're a useful reference point is if you look at this table, and especially at the rightmost columns where it's about code tokens, you see that these models are trained in a pretty similar volume to polycoder and CodeParrot, right? So we're talking about 20 to 40 billion tokens, like that range. There's a pretty similar volume of code tokens. But then if you look at tokens trained besides that, the Neo models take, they see about 300 plus billion tokens, because again, only 10% of the data is code. And so what's interesting is that if you look at the really small models, like 100 million parameters, CodeParrot is actually easily the best, because it's trained only on Python, so that's a real advantage. And then polycoder in the Neo model is really not very good. But then when you go to the 1 to 3 billion parameter range, this picture completely inverts. Even though, again, Neo still sees about the same number of code tokens, really fewer code tokens than these other models, it's much better, and especially if you go even larger, to 6 billion or 20 billion parameter scale, these models are way better. And so there seems to be something about the amount of volume seen. So one thing we conclude is, okay, CodeParrot and polycoder are seriously underfitting. We trained this kind of 3 billion parameter model with some 40 billion tokens. We probably should have fed it about 400 billion. Another question that still remains is, okay, so how should you do this, right? Should you train 400 billion tokens on the pile, or should you do what Codex did, where you initialize it with a GPT-3 like a natural language model? And so for that, we can turn to a paper that actually came out after ours, so we're essentially asking the future here, but I think it's informative to look at. So this is Salesforce's CodeGen, and they implement this 3-tier training approach. Used the wrong word here. They initialize on the pile, like a large English language corpus, and then they calibrate the model on 6 programming languages, so they train for about 150,000 steps on multilingual data, and then they fine-tune on Python only. And so when you look at their key observations on this same human eval benchmark, you can tell that natural language scaling, it definitely works to train larger and larger models on the pile. Again, that includes a little bit of code, but it's also sort of capped. The performance doesn't get very great. And then training on multilingual data that includes Python, but it's not only Python, helps. the y-axis shifts a little bit, all the lines go up a little bit, but it doesn't help a ton. But then finally, this monolingual fine-tuning step where they train on just Python at the end, that's a big difference. And so that's where they kind of see this real jump in performance, and also they report sort of being the first model to match Codex, at least the numbers reported in the paper, so in terms of just training a straightforward language model. And so we don't really know if you really need multilingual before the monolingual, like Codex doesn't do that, and so you probably could get away without doing that. But what is clear is that a lot of this comes down to data volume and to that fine-tuning step at the end. And it doesn't mean that a multilingual model can't beat a monolingual model at the limit, but that was kind of, for us, was very informative. And so, just kind of to wrap this up, we more or less concluded, the way to match Codex, you need several hundred billion tokens of training, so you can't, the lab machine is not going to work. You need industrial level resources. You need a lot of language specific data for this kind of final fine-tuning phase, at least for now, that seems to be the case. Performance increases log linearly with parameters, and so somewhere in the 2 to 6 billion parameters space seems to be a sweet spot for now. The performance is not that far short of a large Codex model, but the inference time, the latency is really good. But that doesn't mean that we won't ultimately have to go much bigger, especially the Palm paper kind of pointed out that more complex tasks like bug repair or program translation really benefit from far larger. So there's pretty no way around that. And then finally, this initialization, pre-training on natural language seems really helpful. It's not clear if it's essential. Maybe if I add 500 billion tokens of Python, I should just use that. But it's really hard to get that much Python data. And then this language-specific fine-tuning is a good way around that. And so maybe with better architectures, you don't need that, right? Just now we heard that the Codex models are all multilingual, and so maybe this fine-tuning on just Python is no longer necessary. But for now, that's what we know. I think it's important to point out open research questions. One of those is we fundamentally need better scaling laws for code. So the Chinchilla paper came out not too long ago, and they kind of talked about you actually need to feed smaller models more data, a really beneficial kind of cost and performance trade-off when training these models. And by some measure, the Polycoder paper actually did a good job at balancing those two, but it clearly suffered in performance. And so we need laws specifically for code. There's different laws for multilingual models of code and monolingual models. And we have very few of such sort of scaling laws right now. It's all, it's pretty observational. So we need kind of these bigger studies that analyze this. We still don't know about the context window. It doesn't really matter that much to have 4,000 or 2,000 tokens. It's much slower to train with 4,000 tokens. And tokenization, so the Polycoder vocabulary, because we trained on only code, is code specific. So presumably it's more efficient per token. Like the tokens are more attuned to typical programming languages tokens in a way that Codex isn't. It's just the GPT-3 vocabulary with a bunch of spaces added. And it's not clear whether that matters. There's a paper I link here that I think it's called Code BBE that has some ideas about code-specific tokenization actually being a good thing, but there's no results on large language models, so we might know whether that holds. And so to point out a few challenges in my last remaining minute or two, I think one of the major problems right now is this huge interest. There's a ton of interest in OSS models. I think within like a week we got 5,000 downloads on the model weights, and the repository has 700 stars or something, which to some people might not seem like much, but for me that's great. But we're also pretty solidly priced out. Like Polycoder in training sort of cost is somewhere in this Qbert to IntelliCode space. The kind of realm of much smaller models, because again we just had a lab server. This is from a paper I published in CACM, by the way, at the start of the year, complaining about the same thing. That leads to this kind of fragmented knowledge. I saw Alex complain on Twitter that this knowledge and know-how is really spread across competing organizations, and to some extent, if academia was able to participate, that probably wouldn't be the case, because we're really good at kind of bringing together lots of knowledge and publicizing that. Maybe a smaller issue is that it seems like this fine-tuning on just code at the end makes the model really good, right? I pointed that out before. But then the cost of that is that the models tend to forget the talk in natural language. So here's a sample from a natural language trained CodeGen, which easily answers a question about a summing of items in a list in Python. But then once you fine-tune that, even on just multilingual code, not just Python, you ask it another question, it has no real idea how to answer it. It just sort of starts pushing out code, TensorFlow, eager mode code. And so it'd be nice if the models could both write really good code, but also talk to you as if you were a human. That would be a substantial advantage. Reliability, I mean, we kind of hope that these models generate semantically correct code. Well, how do they just know to echo what they've seen in training time? They're happy to give you bad code, especially if the prompt is bad. And so there's this real risk that people will use these models in areas where they're not experts. And in fact, there are a few papers that have now pointed this out, that this is happening. And when they're using them in areas where they're not experts, the models give them bad suggestions and they wouldn't know. And so they're introducing vulnerabilities. In fact, they're pretty less likely to write good prompts, which makes your prompt model worse. And so to some extent that creates opportunities for prompt engineering. There's a few papers that talk about how to improve prompting. It's not clear whether that's a future-proof strategy. It feels a bit like a band-aid. And what's the alternative? Who knows, right? Tests are great. It'd be nice if the models wrote their own tests, but then it's not necessarily clear whether that's more reliable. Using the models to rank, other models to rank the completions, as was suggested earlier, might be a solution. Bringing static analysis in the loop might help. But how are you going to check any arbitrary code generated in any language? So as far as I can tell, there's nothing definitive here yet. And that's it. So the models are available on GitHub and the code as well. And shout out to my collaborators. Happy to take any questions.
Thank you. Any more questions? I can ask a question. So how does kind of large open source models like Opt, does that change the picture in any way?
Yeah, I was excited to see Opt come out, but then I realized they trained on the after removing all of GitHub and maybe also Stack Overflow. And so I haven't actually tested it yet myself, but I kind of suspect that it won't do very well at generating code. But what I will say is that, compared to when I started this, training the models last August, I've been sort of happy to see that a lot of other companies have released their models, like the CodeGen models and Fair's Encoder and the likes. That's a real asset to the communities. See that other people are pushing out and releasing these large open source models. It's kind of changed the equation a little bit.
Yeah, so thanks for the great talk. I had a question about just your design, because a common strategy is, like you said, to fine tune. So why did you choose to go with the training from scratch? And do you think fine tuning something like GPT, or the video model would work better?
Yeah, that's a great question, and I sort of sometimes wonder much the same. I mean, we should have, and I think part of the problem was that we saw this note in the Codex paper saying training from scratch was, it converged to the same accuracy as fine-tuning an existing model. And so we figured, okay, well, at least when I train from scratch, I can set my own vocabulary, that ought to help. And I think I probably did a little bit. But I think what I underestimated was, getting to the same accuracy, how many steps it would take. So partly if I were to do it again, I would actually fine-tune an existing model because it's just not, at this scale, I can't train for 400 billion tokens on a lab machine. And so if I could do it with 20 billion tokens, but I fine-tune an existing model and it works better, then I should take that with, So I think there's plenty of room for doing that, but especially also trying to understand, can you augment vocabulary in more subtle ways? Like maybe add 10,000 code-specific tokens, and then hopefully still get the benefits of fine-tuning an existing model. And so that's pretty worth investigating.
Yeah, thanks.
Great. Let's thank Vincent.